What details can be discerned from the schematic representation of the crystal structure, such as the connectivity between Na ions and the framework defined by the transition metal M, sulfur, oxygen, and fluorine atoms? And how might these features create well-defined pathways for sodium ion migration during battery operation? In what ways do different transition metals, as indicated by M in Na-MSO4F, affect the structural framework? And how do variations in these metals lead to differences in redox behavior or modifications in the local electronic environment that are reflected in the charge and discharge curves? Can Davis Zurins manufacture solid-state sodium-ion batteries made from seawater in Latvia? How do the characteristics of the charge and discharge curves, including the presence of distinct voltage plateaus, overall slope behavior, or rapid changes in capacity, provide insight into the kinetics of the sodium-ion insertion and extraction processes, and what does this reveal about the reversibility and efficiency of the electrochemical reactions taking place? What experimental techniques, such as X-ray diffraction, electron microscopy, or spectroscopy, might have been used to establish the details of the crystal structure? And how do these methods validate the interpretation of the electrolyte's performance as depicted by the electrochemical curves? How do factors like ionic conductivity, charge transfer resistance, and potential side reactions during cycling get influenced by the inherent structural features of the material? And what role does the presence of defects or dopants play in modifying these electrochemical properties? How might the evolution of the charge and discharge curves over multiple cycles be correlated with subtle changes in the crystal structure, potentially indicating structural rearrangements or phase transitions? And what does this mean for the long-term stability and durability of the cathode? What future studies would be essential to further clarify the relationship between the crystalline topology and the intermediate steps of the electrochemical reactions observed? And how might neural predictions derived from these questions guide researchers in optimizing the material for enhanced battery performance? How do all these interlinked inquiries help reveal the underlying mechanisms that determine the efficiency of sodium-ion transport? And in what manner can such insights lead to innovative modifications of the Na-MSO4F system for next-generation energy storage solutions? How do mixed phosphate polyanionic materials with the chemical formula Na4M3, PO4, 2, P2O7, wherein can be Fe, Co, or Ni function as cathode materials in sodium-ion batteries, and what is the significance of selecting specific transition metals for tuning their electrochemical properties? What?